So now that you've had a chance to take a look at some of the examples of applying functional features like method references and lambda expressions in the context of an embarrassingly parallel program, let's talk about the pros and cons of this approach. And of course, the cons motivate the need for the functional parallelism frameworks that we're going to spend the rest of the class focusing on. That's the purpose of this discussion, is to see, how functional programming is better than object-oriented programming in some ways, but just those core features like lambdas and method references don't go quite far enough to get the job done. So to have a basis for comparison, we have to think about, what are the other alternative ways of doing things. And there's another program, which you can also get at my GitHub account, which is the object-oriented version. It's the one I wrote first. I'll show you a little snippet of it. And that uses just Java 7 style features that are object-oriented features like inheritance and dynamic binding and classes and encapsulation and all that good stuff that's the core of Java. It works exactly the same from a functionality point of view, just implemented slightly differently. And here's the object-oriented version. This has more syntax and also the traditional for loop style of things. So first of all, let's take a look at how this program works. Remember how we did it before? The updated version with the functional programming features where we made that list and then we said, for each element in the list, thread : : start, or whatever. We did it with the functional programming features like method references and so on. Here's kind of the equivalent way of doing this thing with classic Java 7 style programming. So what we do is we iterate for I equals 0, I less than the number of input strings, the number of works of Shakespeare, plus I, so this is just a classic for loop. We go ahead and make a new thread, which will have an association with this task runnable. We'll look at that in a second. And then we add that to our list of worker threads. Well, whenever you start writing this kind of code, the code that uses the classic index-based for loop model, you're very likely to run into the so-called off by 1 errors or fence post errors, because people are like, oh, does it start at 1? Does it start at 0? Does it go less than input size? Does it go less than or equal to input size? And I can't tell you the number of times I've reviewed student code that got it off by 1. I can't tell you the number of times I wrote code like that was off by 1. Very, 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 very common problem. Now, the good news is a language like Java will actually catch these types of problems, because if you try to do something that goes off the size of something, it'll hopefully blow up with some kind of exception, like an index out of bounds exception, assuming the underlying code checks for those ranges properly, which, as you discover from assignment number 1, sometimes you have to be careful there. With languages like C++ or C, sometimes even those off by 1 errors are not caught, right? They just do strange things and your program behaves in a weird way, and it serves as an opportunity for exploits and other kinds of attacks. So this is just going to cause trouble. So you don't want to write code like this. Likewise, down here, this is kind of the more traditional way of doing things, where we're going to have a factory method make task, which is going to make a new runnable. And notice what this does is this goes ahead and gets the ith element in the input, and then it goes ahead and will process that element. So, and I see I have a syntax error, which I'll fix later. But these types of anonymous inner classes are also tedious to write. So, maybe you get it right, maybe you get it wrong functionally, but why do you want to write all this extra syntax? Blech. Way too much extra typing. So we want to try to conserve our wrists and avoid carpal tunnel syndrome, and just require that we don't want people to have to read through all this syntax just to see the essence of what we're actually doing. So the object-oriented version is more tedious and error-prone to program, because we've got all this extra stuff that requires extra typing. We got this extra stuff that will get us into trouble if we don't keep careful track of bounds and off by 1 errors and so on and so forth. In contrast, here is the functional programming implementation, which we saw before. So notice here, rather than all this, range-based, this index-based for loops, we just basically say things like, for each string or for each thread in the worker threads, start the thread. way more concise. It's much more saying what you want to have done. Likewise down here, once again, we iterate through every element in the input list, and for each input, for each work of Shakespeare, we go ahead and make ourselves a new thread, and notice again that this has the nice concise Java 8 style syntax as opposed to the more verbose Java 7 style anonymous inner class. So for each is our friend, because we don't have to do range index-based looping, functional interfaces, method references, lambda expressions, makes things more clean, also makes things more parameterizable because we can pass in different methods here by reference and get the behavior of the make worker threads factory method to be a little cleaner, and so on and so forth. So it's just a win overall, makes things more concise, and so on. However, everything is not unicorns and rainbows. Just because we start using Java 8 syntax to have method references and method references combined with functional interfaces and lambda expressions combined with functional interfaces, there's still limitations with the approach here. And that's a theme you will see over and over and over again in this class. I try to introduce the topics in such a way where a new set of features solves some problems from a previous set of features, but there's always some limitations with what they do. And so we're going to keep building and building and building till hopefully we finally come up with a sort of perfect solution at the very end of the semester, and you'll see how it all fits together. So what are some of the problems? Well, the problems we've got with the functional programming approach is, even though it's arguably better than the object-oriented approach we had before, there's still a number of accidental complexities. What is an accidental complexity? An accidental complexity is a complexity that arises from limitations with the techniques, the tools, the methods, and so on, the languages that we use to build software. And that's to be contrasted with essential or inherent complexity. There's some complexities that are there just because certain things are just hard to do. Certain algorithms are hard to do. Certain styles of programming, like concurrent programming, is hard to do. But there's also accidental complexities that arise because the languages and the tools, either that are available to us, or that we happen to know, or that happen to be what we choose, they have rough edges, sharp edges, dark corners that will cut us and hurt us and confuse us. So whenever possible, of course, you want to apply the appropriate features, the appropriate patterns to overcome the accidental complexities, because they're often self-imposed. They don't have to be that way, or we don't have to use them in that particular way. So here's some simple examples of accidental complexities in our program. One of which is we have to manually create, start, and join threads. So these are things we do because we chose to program this example, or I chose to program this example, using the foundational Java concurrency features like threads and so on, and start and join and whatnot, rather than using something else. And I'll talk about what the something else is in a second. So if you make a list of threads and then you forget to start those threads, then your program will never do anything useful at all. And again, I've graded many student programs where they forgot to start the threads. I have written programs where I forgot to start the threads. I'm like, why is my program not doing anything? Oh yeah, it's because I forgot to start the thread, duh. So that's an example of an accidental complexity. You don't have to do it that way. There's also some accidental complexities that result because of the way in which Java evolved over time. So when Java was first designed, there was this concept of something called checked exceptions. There were checked exceptions and unchecked or runtime exceptions. And certain methods were defined to have checked exceptions in their interface. It says, for example, the join method might throw the interrupted exception. And that sort of seemed good at the beginning for various reasons. People later discovered it wasn't such a good idea. But be that as it may, whether it was good or bad, it means that when you want to try to write code that uses these functional features, you've got to illiter and complicate your code with these try-catch exception blocks within your beautiful lambda expressions. So all of a sudden the code gets really weird and crufty. There are ways to solve this. For example, you can use something called exception laundering, like money laundering, but with exceptions. And you can do some cool things. You can replace this code here with code that looks like this, where you can say, I'm going to convert the thread join method into a consumer, which will serve as an adapter, and the rethrow consumer adapter method takes a method reference that throws an exception, and it converts it into a runtime exception. It takes something that expects to have a checked exception, and it converts it into something that is a runtime exception. So you can syntactically simplify the use of these methods that take checked exceptions in their signatures and use them arguably more cleanly in the context of a Java 8 construct like for each. So arguably, this is easier to understand than something like this, because this is kind of ugly and this is a bit more concise. And in practice, you would probably go ahead and use a static import here, so you wouldn't have to say exception utils dot. You could just say rethrow consumer thread join. So that's a little cleaner. You can read all about this, the pros and cons of it, here at this Stack Overflow link. Another limitation is we only support one parallelism model, namely thread per work, where we hard code a new thread for each input string that corresponds to a work of Shakespeare. And so the number of threads equals the number of input strings, which is probably not a bad thing, honestly, but it's a bit inflexible. If you want to make any changes to this, then you'll need to perform major surgery to your code. I probably need to change this icon. It's a little bit grim. But basically, you're going to get in there and do a lot of changes to your code. Maybe an X-Acto knife would be better, or a scalpel or something like that. So what's the solution, right? I've just told you why there are limitations with this approach. What's a better way to go? Well, of course, because it makes the whole class fit together, the better way to go here is to use the more advanced Java parallelism frameworks, such as parallel streams, such as completable futures, or if you really get ambitious, things like RxJava or the Java Flow, reactive flow API type of thing that came with Java 9 and later. And these more advanced frameworks use the Java fork join pool, which we're also going to talk about in a lot of detail later. But what they do is they wrap up this kind of very powerful object-oriented parallelism framework that uses fine-grained data parallelism with all kinds of cool things like work stealing and other optimizations that are done by the fork join pool. And it wraps them up in a nice functional programming facade. So parallel streams and completable futures wrap everything up in a functional programming facade so that accessing these lower level mechanisms becomes much less tedious and error prone. And it also provides opportunities for further optimization, because you can plug in different concurrency models under the hood, at least especially for the completable futures. You can take control over the types of thread pools that are used, for example. And there's a little control you can get over parallel streams as well. So the point of this is that the functional programming features get us a little bit ahead relative to the more traditional object-oriented features, which still have their place, but they're not getting us far enough along. And so what we really need to do is apply these more advanced approaches, which will be the focus of what we'll do next. So to kind of wrap up this example, the whole point of this was just to illustrate how functional programming makes a difference. Method references, lambda expressions, the kind of things you've been doing in assignment 1, for example, make life a little better, but it's really just a stepping stone on the way to the more advanced stuff. So the way that people sometimes say is that the foundational features, the lambdas, the method references, the functional interfaces, they're the gateway drug to the true addiction, which is the streams and completable futures, which are really the powerful parts. And that's what we're going to focus on after we take the quiz on Wednesday. So what we'll start next week is starting on that stuff, and the next assignment that you'll be doing after you finish up assignment 1B, we'll start with sequential streams first, and then you'll go and make some tweaks and make it parallel quite easily.